Hey there, everybody. So we're into the second PowerPoint dealing with waves. Altogether, this is, I believe, the fourth one. As I said, this is going to be very similar to what we talked about before with the harmonic motion, seeing as waves abide, or at least the waves we're going to talk about, abide by harmonic motion. So that going. So just straight up, a wave, by definition, is something that creates a disturbance that results in energy being transformed from one point to another. Now, mechanical waves are the type of waves that specifically require a medium in order to propagate. Basically, they need something to actually disturb for the energy to go from one point to another. So one good example is a water wave. If you've ever been in a water wave, there's this disturbance in the water at one point, the energy transfers over to another point. Or if you've ever played on a string, you can move that around. A wave goes from one point to another, transferring only energy. Now, sometimes we use a different term. A lot of times when we talk about a wave that is a single disturbance, we're usually referring to a pulse. That's what we kind of call it. But if it's a wave that is continuously disturbing the medium or doing it in a periodic motion, that's what we usually call as waves. So usually when I'm saying waves, I usually am referring to continuous disturbances. So this is just one example of a wave. You can have a string and it's a single disturbance or a continuous disturbance that causes the string to go up and down. There are some parts of the wave that you need to know, like for example, the crest is the highest point, the trough is the lowest point, and then the amplitude is the height or the depth of these points, of either the highest crest or the depth of a trough. Then we also have something called wavelength. As its name implies, it is the length of a wave. So for the wavelength, you have to make sure that you go from one point to the very next point that's identical to it. So for example, if I start at a crest here, my wavelength will end the next time I get to the next crest. Likewise, if I start at a trough, I have to go to the next trough for one full wave. I don't even have to be at those points. If I want to be right here, a little bit to the right of a trough, then I would end a little bit to the right of the trough. Now, this is going to be our main equation for a lot of waves. It's V equals F lambda, or frequency times wavelength. That's what this lambda is referring to. It's the wavelength measured in meters. We could also use lambda over period since of the inverse relationship, but for the most part, you're going to be using F lambda more often than not. This is our main equation. And then these two equations still hold true from the other. Basically, that frequency and period have an inverse relationship. Now, there are two different shapes that mechanical waves can come in the form of. Um, this just kind of says, again, relating it back to what we talked about with the harmonic oscillators. Remember how harmonic oscillators, the spring will go back and forth between an equilibrium position? Well, that's pretty much what's going on with the wave. It's going back and forth between an equilibrium position, which is this line right here. All right, so the first type of wave that we have is a transverse wave. Now, a transverse wave is one where the medium is going to end up moving perpendicular to the wave motion. So the wave moves, let's say, to the right. It's going to cause the medium to move up and down, perpendicular to it. That's actually very similar to what we had in the animation before. Uh, but one way to identify transverse waves is that they look like sine and cosine waves. They look like trig functions. Like this wave looks like a sine curve. This one looks like a cosine curve. So that's one good way to identify them. Now, what we need to do is we need to come up with an equation to determine the speed of a wave and try to think about what variables will affect it when we're talking about transverse waves. Like I said before, the v equals f lambda is a very generic equation. It works all across the board. However, for transverse waves, there are properties that are going to affect its speed. Now, I'm just going to briefly run through the derivation, like I said, just so that you have a brief idea of how we're coming about this. So, if you can consider a rope being pulled from a wall, it's going to be experiencing some sort of tension to pulling it to the left. And then when the wave starts moving in, the wave will actually start being lifting the rope upwards. That's what's going on here. So we have a relationship between the tension pushing it horizontally, the uh, distance that it travels horizontally, and then also the force pulling it upwards and the distance it moves upwards. So we can come up with this ratio, simplify it a bit, move some things around so that we have FYT here and FTT over there. Then what we can do is just talk about how um, FT is just a change in momentum, which is m times v. So plugging this stuff in, we can simplify this equation. So it looks like this by combining this with this equation up here. Then one thing that we want to actually do is we want to replace m of the wire with mu times length. That's what vt is. Velocity times time gives us length. Uh, Mu is actually referring to the mass per unit length, or sometimes called the linear mass density. It's measured in kilograms per meter, and it's, as its name implies, it's mass per unit length. But mainly the idea is that this makes our life a little bit easier because a lot of times, for let's say you're talking about a string usually has some very defined linear mass density. So instead of just massing the string, which is for the most part usually very small, what we can do is just mass the whole thing, find its linear mass density, and then when we're working with it, we could just measure that length in order to quickly figure out its mass. So it's just a shorthand. Like I said, it's usually used a lot more because of the fact that it's a lot easier in lab situations. So when we play with this equation, moving things around, we end up getting this for the velocity of the wave as it moves through a string. So this is a transverse wave equation. All right, when you record this equation, make sure that it's strictly for transverse waves. But it basically says that it's related to the square root of the tension in the string over the linear mass density. All right. So let's practice that real quick with this question, and then we'll go over it in a second. Okay, so what we're going to do is, well, they talk about a bird landing in the middle. Now, sometimes it's easier to try to draw this out to visualize it, but we have a bird in the middle of this wire, lands right in the middle, and a pulse goes from the bird to the end and then back. So it's landing about 40 meters from each side. So the pulse is going to go 40 meters and then 40 meters within that 0.75 seconds. This is going to play a part in a second. So now what we're going to do, we're going to use our equation and rewrite it in terms of tension. Replace mass per unit length in for mu. They don't tell me they tell me the length, but they don't tell me the mass. However, with the density and this diameter, I can figure it out by replacing mass with rho v. And then I could also split the volume up into the cross-sectional area times the length. That actually helps me out a lot because it drops out the length in here. And then replacing pi r squared for cross-sectional area. And then for the velocity, like I said, we're just going to do the distance over the time But the nice thing is that the distance is the full length of the string because it goes there and back. So from the middle to one end and then back to the middle. And then the total distance, total time is covered in this amount of time. So plugging these two back into here, I end up getting this as my equation for the tension, plugging my numbers in, and I get that the tension in the wire is 353 newtons. All right. Now the second type of wave is a longitudinal wave. Now longitudinal waves are different because now they're going to make the medium move parallel to the wave motion. So instead of moving it up and down, it's going to move it horizontally with the direction of the wave. So this is what a longitudinal wave looks like. So here, this just has a platform that's moving side to side, and it's causing the wave to actually move to the right. You can see that if you just pick one particle, it's always going left and right. The overall number of particles is going to remain the same. It's not like it's going to start building up over here over a period of time. It's just going to, these particles are going to constantly go back and forth. This is what it looks like for a spring. Typically, drawing out longitudinal waves are a lot more complicated and they look a lot messier. So a lot of times what people will do is they'll actually redraw longitudinal waves as transverse waves, just by usually using the whole idea that these areas of compressions act very similar to crest, and these areas of expansions in between them would represent something similar to a trough. Now, wavelength is done the same way. You still go from the max, like from one point to the very next point. So the middle of a compression to the next middle of a compression, or middle of expansion to middle of expansion. Now, if we want to find the velocity as a wave moves through a medium as a longitudinal wave, we have to use this equation. Now, this, if you actually kind of think about it, is very similar to the equation that we just got for the tension. You know, if we think of the tension as being a factor of the medium itself, like in this case for a longitudinal wave, since it's all about how the medium is able to compress and elongate, well, that's kind of related to something similar to elasticity. And then it was divided by the mass per unit length, which is essentially the inertia factor. So we can use that as like a blueprint for what the velocity would be for a longitudinal wave. And when we kind of use, bring back what we talked about in the first topic when we were talking about Hooke's law and Young's modulus, what we could do is for a solid, our equation would look something like this, where we would use the Young modulus elasticity value that we have and divide it by the density of the material. Or if we're talking about a fluid, we replace that with the bulk modulus, but still dividing it by the density. So depending on what medium it's traveling through, whether it's a solid or a liquid, solid or a fluid, we would use one of these two equations. But again, it looks very similar to the transverse wave, so that's kind of nice. Just make sure that you identify that first, that these are both longitudinal waves, and that each one is for a different type of medium, solid and fluids. All right, so here's another question. You could try this out yourself, and we'll go over it in a second. All right, so this one is actually very similar to the previous one. Well, at least for, I think it's for part B. So for part A, they want us to figure out the wavelength of this wave. What we're going to need first is to figure out what the speed is. So like for example, of our equations, there's only one that deals with wavelength, and that's v equals f lambda. We have the frequency, but we don't have the speed. So we're going to have to figure that out. So we use the equation that we just got, the one with bulk modulus, since we're dealing with the C, fluid. and then we plug the numbers that we're given to get that the speed inside the water is about this 1,400 meters per second. Then we can combine that with the v equals f lambda equation to get that the wavelength is 14 centimeters. All right, now for part B, they want us to determine how long it takes for the animal to detect its own reflection. So we're going to go back to the very basics of speed, that it's distance divided by time. We know what the speed of the wave is, so we just need to know the distance. Now the obstacle is 100 meters away from the bat, but just like, or the animal, sorry. But just like with the bird, the pulse that's being emitted by the animal is going to go from it 100 meters to the obstacle and then back to the animal. So it's going to do double duty and go 200 meters. So we have to double that distance, and we get that it would take 0.14 seconds. All right. Now we talked about how waves are transporting energy, so let's go a little bit more into that. Now, once again, this is going to come up. I'm going to do a little bit of a derivation, but I'm going to also bring up a bunch of different mini equations. Just as I said in the previous topics, when you're doing these questions, you want to try and make sure that you're picking the equation that works best. A lot of times we're going to be using the final equation that we're going to get to, but every now and then they might throw in information where it might be easier to use one of these in between steps. So a lot of these equations actually still work. Now, if we think back to the fact, like I said, there's this connection between waves and the simple harmonic motion, so we can actually go back to what we mentioned before with the harmonic oscillators and how the total max energy was related to 1/2 Ka squared, where K was the spring constant and A was its max amplitude. However, the thing is there's no spring involved here, so we're going to want to try to get rid of this spring constant. So we can actually think back to some of the other equations we had for spring constant. Like for example, we had that one for the angular frequency that was omega equals rad k over m. So what we can do is just rewrite it in terms of k and then replace the angular frequency with 2 pi f. So what I'm now going to have is this, which I can kind of replace the k with. So now it's in terms that any medium has. Like for example, when the wave's going through, it has a defined frequency and the medium does have a mass to it. So this equation is now going to make a lot more sense than the original one. But notice how it is still coming down back from that original basics that we had before, that foundation. So simplified, the equation of energy would look something like this. Now, like I said before, as we're talking about the wave moving through a medium, a lot of times it's not really useful to talk about mass since, for things like lengths and volumes, three-dimensional waves, transverse waves, all those things, it can be kind of pointless to talk about it. So we'll switch mass with density times volume. And then what we're also going to do is we're going to consider a case of a wave passing through this imaginary block. So the volume will end up being the cross-sectional area and the length. The length can be replaced with Vt, so it's relating to the speed of the wave. And then we're using S as the surface area. Normally we would use A, but we don't want to confuse it with amplitude. So that's why we're using S for surface area. Again, taking this and plugging it back in for M, we end up getting this equation. And this basically shows that the energy of a wave is going to be proportional to both the frequency and the amplitude squared. So this is actually a pretty important thing later on, and it's going to end up resulting in a conflict when we start talking about electromagnetic waves. because it will turn out that while mechanical waves do have this squared relationship with amplitude, electromagnetic waves don't, and that results in a big problem. All right. Now, with that equation for energy, we can actually get two more different types of equations: power and intensity. So, the power one's easy. We take this energy equation and we divide it by time. Boom, there we go. So, essentially, this T drops out. So, the equation gets a little bit nicer, not significantly nicer. So, this is another equation that you're going to be talking about, typically average power. And then another thing that we're going to talk about is intensity. So the intensity is this power which is being given off by the wave, but then dividing it by the surface area that it's traveling around. This can be thought of as like if you think of um, a source that's emitting a wave, something like a speaker that's emitting a sound wave going in all three directions, we can think of the surface area that it's reaching as being that location, like the circle around it at some radius. So we can divide it by S to get this equation, or we can also remember that intensity is the average power divided by 4 pi r squared. This is going to actually give us an important thing, that the intensity has an inverse square relationship with radius or distance. So when you double your distance, you drop your intensity by a quarter. I think this is, we actually use something like this for astronomy. In astronomy, we use this for the light intensity surrounding a star using the inverse square law. We can also use this for things like, the standard candle and all these other things for astronomy. So this actually, like I said, is a very important relation, and you would definitely want to make sure you write this down. So in addition to like this equation, this, and these two, I would definitely record this, as well as this one's a little bit more minor, but basically the amplitude has just a regular inverse relationship with distance. This one also can be used. So we'll try using some of those equations here. So pause the video, work on this yourself, and we'll go over in a second. All right, so they give us some information, they give us a distance, and they give us an intensity. And what they want to know is the intensity at another distance. So this, because I don't have any other information, what it seems like I'm going to want to do is some sort of relationship. I want to come up with some sort of proportion. Now, make sure that you don't make the mistake of doing something like this, where you say the 100 kilometers is equal to 1 times 10 to the 6th, and then divide the 100 by 400, and then set it equal to the 1 times 10 to the 6 over x, and use that and be like, oh, well, the distance got quadrupled, so the intensity should get quadrupled. That's not how it works. Remember, they have an inverse square relationship. So the equation I'm going to use is this from that inverse square relationship. Solve it for I2. Plug my numbers in. I don't really have to worry about getting these units the same. I don't have to convert them into proper meter units because they're both in kilometers. That's all that matters. But I ended up getting that the intensity increases to 6.3 times 10 to the 4th. So it drops a significant amount. All right. Next, we're going to talk about the traveling wave equation. So similar to what we did with the harmonic motion, where we wanted to come up with a very generic equation to talk about, where would the object be after a certain amount of time, we kind of want to do something similar. So we want to talk about, well, what would be a good equation for a wave as it's moving through a medium? Well, first, we're going to start off with this very standard equation. clearly this looks like a sine curve. So what we're going to say is the displacement, the vertical value of the medium, well, let's call this a rope, at some position x, so some position along the rope, is going to be equal to the amplitude of the wave times sine, because this is a sine curve, uh, and the angle that we're going to do is 2 pi over lambda times x. All right? Because we get one full wave is going to be one full sine wave is essentially 2 pi radians. So that's where this is coming from. After one full wave, this becomes a full equal 2 pi over 2 pi essentially, and it starts over again. So we're going to start with this. Now, what we want to do is we want to take into the fact that this wave is moving to the right. So after a while, this is going to get shifted over a bit. So we're going to do pretty much something where we're going to say, well, after a certain amount of time, if it's moving for some speed, it's going to shift by a distance of vt. Just like you would for any sort of graph, we're going to take x and subtract this vt term, the amount that it's going to move horizontally. We can distribute the 2 pi lambda over to here, and now what we can do is replace the v lambda with another term, with frequency. We're also going to do something similar over here. So we're going to replace the 2 pi over lambda, and we're going to define it by this k term, which is referring to wave number. Now make sure that you're noting that this is not spring constant k. It is not at all related to it. This is wave number, just 2 pi over lambda. Again, kind of playing with the whole idea that one wave is within 2 pi radians. Likewise, like I said, we could do something similar here. Replace the v lambda with frequency based off of that first equation from this video. And then we end up also replacing frequency with omega over 2 pi. So this will then simplify to this. A sine kx minus omega t plus phi. Now we still have to include this phase shift for the exact same reasons as before, because even though we're saying it's a sine curve, you never know. It may have started at some other form. So it could have started as a cosine curve, could have started somewhere in between. So we still need to take this into account, but just like before, most of the time it's probably 0. Other times they'll tell us the initial conditions, and we're going to find the phase shift the same way. This is sometimes referred to as phase velocity, just taking the wavelength, dividing it by k. Pretty much the speed of the wave and how it's affecting the phase. One thing to note that this sign here, if it's traveling, this is for a wave traveling to the right. If it's traveling to the left, you make this positive. So pay attention to the sign. And that's phase shift, like I said before. All right, so I'll try that out here. Basically combining all the equations that we learned, and we'll go over it in a second. All right, so what we're going to do, they want us to find speed, wavelength, and this term. Based off of what's given to us, the fact that we're talking about a transverse wave, what I'm going to do is use the force and the linear mass density to find the speed. So I get 34 meters per second there. Then what I can do to find the wavelength, well, now that I have the speed and I have the frequency, I can combine those two to find the wavelength using v equals f lambda. And then here, where I'm going to find the equation for the position of the wave at any position in time, I'm going to have to make sure I use this. So the fact that it has an amplitude of 2.6, but it's starting at a height of 1.6, tells me that there is going to be a slight phase shift between that. So I'm going to end up having an initial phase shift. So I'm going to set this equal to 0. So I'm going to set x and t equal to 0, which drops this entire kx minus omega t term. And I get 1.6 equals 2.6 sine of phi. Solving, I get that sine is 38 degrees or 0.66 radians. Now remember, in the previous scenario, I had made the comment that you wanted to pay attention to which quadrant you're in, whether you're in quadrant 1 or quadrant 2. Um, I think in this case, I don't know if there is enough information for you to figure out which quadrant you're in. So we're just going to stick and say that's quadrant 1. Um, for the most part, the only difference would be whether this is plus phi or minus phi. I guess what we could do is use this diagram here and say that since we're dealing with the sine curve, this is quadrant 1. So I can stay in the 30, I could actually keep this as 38 degrees. So what I'm going to also do is I have to figure out what k is and omega is. So k again is using 2 pi over lambda. So you get 45 for that. And then the angular frequency is going to be 1570. So our full equation is going to look like this. Now notice I did end up dropping a lot of the signs. That's fine. Just make your life easy. All right. So very similar to what we did before, where when we were talking about the harmonic oscillating equation, we had to come up with that equation of motion to verify that cosine was a viable equation for the harmonic oscillator. We're going to do something very similar here. So what we're going to do is basically look at the forces going on in the y direction. So sum of forces equals mass times acceleration. We could do the same thing that we did in the previous topic where we replace acceleration with the second derivative, but we're going to do it of not just of some generic x term, but of the displacement equation that we have. Then we replace mass with this mu term, this mu times x, so because that equals to mass. Then what we can do, if we look at this diagram, the vertical tensions or the vertical forces are equal to the tension times sine. That gives us the vertical components. We can use the small angle approximation and say that since these angles are really, really small, that sine of theta is approximately equal to tangent of theta, which is actually about equal to this slope. If that just comes from the fact that, again, tangent is change in y over not change in y, opposite over hypotenuse, opposite over adjacent, which is similar to the slope equation, which is change in y over change in x. So you know what, I'll just write it here. So if you remember SOHCAHTOA, your tangent equation, it's opposite over adjacent. And like I said, if you use this for a triangle, this is your opposite term, this is your adjacent term. That's essentially y and x. So change in y over change in x. So that's why I'm replacing it with this first derivative. That's the slope. All right. So what I can do then is just say, well, that's just slope 2 minus slope 1. Again, just to kind of combine and simplify things. We can divide this delta x over, and so we have a change in the slope over change in x. Well, since slope in this case is defined as delta d over delta t, this just turns into, when we take this the limit, ends up being a second derivative of the displacement as a function of x. So recombining these two equations together, we end up getting this. So this equation is the one-dimensional wave equation. But I just wanted to point out what this is actually referring to. Just like the first equation of motion from the last video, this equation is really meant to see if the equations we have are viable wave equations. Will the equations we're using make sense based off of this? If it satisfies this condition, then it is an equation that describes a wave. If it is not able to verify this equation, then it's not an equation. For example, if you tried something like setting the function dx dt being equal to something like 5x cubed plus 3t squared, and you use this equation here, it's not going to satisfy this. So you would say that this is not a good equation for a wave because it's not satisfying this condition. So yeah, this is a condition for a wave. So this is just showing how that formula that we just found before fits into the wave equation. So remember, this is our wave equation. We're going to have to first take the first derivative of it with respect to x. So this sine turns into a cosine, and this x gets taken the derivative, and the k comes in front. We take a second derivative of it, and it becomes negative k squared a times this sine. Do the same thing, but this time for time. So we're going to have this omega part coming in. So minus omega here, times it by another negative omega, and it turns into this. When we recombine this, put it in for the second derivative with respect to x, and this, the second derivative with respect to time, we end up getting this equation. We can get rid of a lot of things. We could get rid of the a on both sides. We could get rid of the sine term from both sides. And what we end up getting is, hey, v squared equals omega squared over k squared, which, as we said before, is an equation for the wave. So that means this equation works. The fact that we ended with a true statement at the very end tells me that this makes sense. I believe one of your homework questions, I'm going to give you another equation, which is completely like, I think it's got an e function in it. And basically, I want the same thing. I want you to figure out, does it satisfy our wave condition? So you're going to do the same thing I did up here and see, do you end up with the same results, that v equals omega over k? All right, so we're going to stop the video right there. And then we'll continue it on tomorrow. So I'll see you in the next video.